So I'm going to go through some of the simplest use cases of PyBaMM. So creating a simulation and running it and plotting some of the variables, and then combining different simulations and saving them, and finally setting up an experiment like CCCV or GITT. So first thing we're going to do is install PyBaMM. So first I'm going to create an virtual environment and then activate it. And now I can install PyBaMM through pip. And what this does is it automatically installs all of the dependencies, so NumPy and SciPy and Casali and all the other ones, and sets everything up for you, and it should work well on Mac, Linux and Windows. Okay, so now we can start the Jupyter Notebook, which is a nice interactive interface for showing some Python examples. So I'm going to go through the results in this running simulation, and you can actually find this repository over on PyBaMM. So if you go to PyBaMM and then go to our team repository and then workshop notebooks, you can find all of the notebooks here. I'm going to go through the first simulation and experiment, but I'll do the same thing in a new notebook, just so I'm typing as I go along. So first thing we do is import PyBaMM, and hopefully the installation's worked okay, and that just runs. Okay, great. So now I'm going to set up a PyBaMM model. In particular, I'm going to use the lithium-ion DFN, and then I'm going to create a simulation using that model, and I'm going to solve it, and finally I'm going to plot it. And so what that does is it creates this interactive plot where variables that depend only on time, it shows the whole variable as a function of time, and variables that depend on time and space, it shows a snapshot of the variable as a function of the spatial variable, so here x, and as you move this slider, the spatial variable changes, and this dashed line shows you where you are in the time variables. So as we go along, we see the negative electrode discharging, well, both electrodes discharging, but the concentration decreasing in the negative particle and increasing in the positive particle. And we see these concentration gradients in the electrolyte. Okay, great. So something else we can do is define different models or pass options to models. Now the information on this, you can go to the PyBaMM repository, and then if you click on the URL here, it takes you to read the docs. And if you look at base models, base battery model, you have all of the different options you can pass to the model. So the one I'm going to do is the particle option. I'm going to do fast diffusion. So let me create a new simulation, a new model, call it model fast, and again it's going to be the lithium-ion DFN, except this time I'm going to give it the options for particle to be fast diffusion, and also I'm going to call it fast DFN. And now I can create a simulation for that model, which is again just calling PyBaMM.simulation, and this time passing model fast. And then we can solve and plot. And again, this just gives us the results for the simulation with fast diffusion. Now, what if we want to, instead of having these two individual plots, compare the two different models? Well, what we do is we call the function PyBaMM.dynamicPlot, and then give it the two simulations, so have sim and sim fast. And now it automatically just plots the two simulations on the same plot. And now we can look at what's happening and compare the two simulations and look at differences, and we can see that with fast diffusion the particle concentrations are different, and therefore the voltage is slightly different. We're also not held to account to just these variables. We can plot whichever variables we want, and to do that we have to pass in the variable names to this plotting function. So say I want to plot, okay, I only want to plot the negative particle surface concentration and the terminal voltage in volts, and maybe I want to compare what the currents do. So I'm going to plot the electrolyte current density. Now it's only going to give me those three variables, and I can again compare what those variables do. And the other thing you can do is if you pass in a sublist where you put in two variables together, you can compare those two variables on the same plot. So now this final plot is showing me both the electrolyte current density in the solid line and the electrode current density in the dashed line. And we can also do this with something like reduced order models. So something Rob showed was the different reduced order models we have. So the SPM, the SPME, and the DFN. In this case, instead of manually making three simulations, you can do it in a for loop instead. So for each model, I'm going to make a simulation, then solve it, and then store that simulation in the list of all simulations. And then again, I can call dynamic plot to plot all the simulations together. And so here you can see the classic thing in the comparing the SPM and the DFN, which is that the SPM in red has no spatial variations in the electrolyte, and so the voltage is a bit off, but then the SPME captures the DFN's behavior much better. And down here is telling you which model is which. Again, just to show you this again, we can compare some different variables. So maybe I want to just look at the temperature. So what I can do is I can go back and add some thermal effects to the modulus. And then I want to solve, if I want to plot the temperatures, I can look at the x averaged cell temperature. It's taking a bit of time with the thermal effects. And now it's just showing me there's the x average cell temperature. Okay, it's a bit boring because we're doing quite a low C rate here. But just giving you a flavor of how easy it is to quickly investigate different effects and then look at different variables in the model. Okay, so once you've solved the model, you can obviously just do this quick plot, but you might want to save the model so that you can come back to it later, or you want to export it to a different format. And that's also very easy to do. So I'm going to start again making a new model, this time with the SPM, and then make a simulation for that model. And solve it. Oh, lithium on. Now say that I'm going to come back to this later and I want to just save my simulation. So I'm going to save it. I'm going to call it spm.pickle. And then later on, say I come back to this and I want to load it. So I load a new simulation. And I load it using the file I've created. And now I can plot this simulation. And it's giving me the results of the SPM. Maybe what you want to do is say, instead of saving the whole simulation, you just want to save the solution object, which is a bit smaller and doesn't keep track of all the parameters and discretization that you used. You can do this too. So I can extract the solution from the simulation, which is just sim.solution, and then save spm solution.pickle. And again, now if I come back to this later and I want to just load the solution that I've saved, I can just use the same command, PyBaMM.load spm solution.pickle. And then I can plot this solution. And again, it's the solution of the SPM that I just created. And maybe you don't want to save the whole solution object to pickle file. One reason why you might not want to do that is because if the API changes, then trying to load the solution up again might cause some problems. And instead, you can just save the underlying variables that you've created as a pickle dictionary. So to do that, instead of calling sol.save, you need to call sol.save data, and then give it the name of the file you want to save. And now you need to give it which variables you want to put in a dictionary. So for example, I can say I want to save the current and the terminal voltage, and maybe something that depends on space, so the electrolyte potential. And now if I load this sol.data.pickle, it's going to give me this dictionary where the keys are the variable names and the values are NumPy arrays, and they're 1D arrays for the variables that depend only on time, and they're 2D arrays for the variables that depend on space as well. And the final thing you can do is, instead of saving to a pickle file, you can save to a CSV file, which you can then read into any other software that you want. At the moment, you can only do this with the 1D variables, so things like time and current and voltage. So say I want to save the time, the current, and the voltage, and save this as a CSV file. Okay, so it doesn't know what voltage is. I have to give it, so terminal voltage. And now I've made the CSV file, and the CSV file, the rows are going to be, each column is going to be one of the variables. So I have my time, and then the current, and then the voltage. Okay, so that's very basic how you create a simulation, and then how you can plot and compare different models, and then save your results. The next thing that is hopefully useful to many of you is creating some experimental protocols. So I'm going to do this in a new notebook. And again, I'm going to start by importing PyBaMM. So the first one I'm going to look at is the CCCV. So the way to do this is there's this experiment class, and the experiment just needs a list of instructions written in a fairly specific format, but easier to read. So first I'm going to discharge at 1C until I hit 3.3 volts. Then I'm going to hold at 3.3 volts for 1 hour. And then I'm going to charge at C/2 until I hit 4.1 volts. And then I'm going to hold at 4.1 volts until I hit 100 milliamps. So now I've created this experiment, and I can just solve a model with this experimental protocol by a very similar command to before, the model I want to solve. Then I make another simulation object, and I pass in the model, and this time I also pass in the experiment with the keyword experiment. And now, again, solving this is as easy as just calling sim.solve. Then I can plot various things like the negative particle surface concentration, the terminal voltage, and the current. You might notice that I didn't put any units here, and basically what happens is if you don't put in the unit, it plots the dimensionless variable that goes between 0 and 1. If I had put in units, it would give me the same variable, but with its dimensional units. And so we see we get the what we expected, so we get the constant current discharge, and then the hold, and then constant current charge, and then the hold. Now, what if we wanted to do this again, but with multiple discharge and charge? Well, because of the way Python lists work, all I need to do is multiply this list by 3, and it's going to repeat this list 3 times. Oh, maybe not. And I'm going to get 3 cycles of discharge and charge. And you can see now the negative particle surface concentration going down and back up as we discharge and charge. So basically, this is useful for quickly running a model with the same experimental protocol as you run an experiment with, and then investigating how some internal variables vary during that experimental protocol, and also making sure that the model matches reasonably well with data. So some other experiments you can do. Really, you're free to combine any of these strings in whatever order you fancy, although as you saw, it can be sometimes a little bit fiddly. But some of the standard ones, for example, you can do a GITT. So going to make an experiment which is going to be some low current discharges. So discharge at C/20 for 1 hour, and then rest for 1 hour. And I want to do that 20 times. And then I can just copy these commands again to solve with now this new experiment. And then I can plot the terminal voltage and the current. And so we get the classic current on, current off from GITT. The last thing I want to show is that you really can combine any crazy strings that you fancy. So I'm going to do some pulse charging, where I'm going to start by doing a constant current discharge for 20 hours. And then I'm going to add, so adding lists in Python just stacks all the lists together. So I'm going to add charge at C/20 for 30 minutes, followed by a high C rate pulse for 20 seconds. And this one I want it to give me finer control, so I'm going to tell it to record every 1 second, and then rest for 20 minutes. I'm going to repeat that 5 times, and then finally I'm going to finish charging the C/20 until I hit 4.1 volts. And hopefully okay, maybe that was a bit ambitious. Okay, I actually don't know what I've done wrong there, but anyway, that's the perils of live programming for you. You can, if you go into the experiment notebook, hopefully you can see it in action working. There you go. So you get the 5 high current pulses, and then the relaxation, and then finishing the charge up to 4.1 volts. Okay, so that's it for me. I think the plan was to have a small break now. So let anyone catch up if they have any questions or grab a drink or something, and then Scott's going to talk about some more options that you can do past the simulation.
When would do we resume?
In 5 minutes.
Okay. See you in 5.
Yep.